So is Kailash? Yeah, you're here. Can you please share your start sharing your screen
Hello? Yes, sir.
and just start when you're ready. Just give the talk. We can hear you. I just heard you speaking. We can't see you though. We can't see your
Yeah, sure,
talk
sure.
yet.
Okay, sir. Yes. Yes, sir.
Okay, we can see it. We can hear you. So please start.
Yes, sir. Sure. Yeah, am I audible so clearly?
Yeah, you are. Yep.
Okay, sir. Thank you, sir. Thank you so much for this opportunity. Yeah. So, yes, sir. I'm Kailash and Swami, working under the Professor Shantanu Kole in the Department of Mathematics, Birla Institute of Technology and Science, Pilani, Hyderabad campus. Yeah, so for this workshop, the title for my work is Mathematical Modeling of Scholastic Floating Flexible Membrane Placed over Variable Bathymetric Region under Oblique Waterways. So, yeah, here is what. Yeah, so this presentation's overview will goes like this, where I will introduce with the problem which I have done here, followed by some objective, then mathematical formulation, followed by some results and conclusions. Yeah. How we can say why we need the breakwater, like what the use in the real life. So actually breakwater, why we are using breakwater to protect the shoreline and harbors, because breakwater absorb and reflect the energy of incoming waves, and it reduce the impact on the coastline of the harsh, we can say harsh water force. And also with this, with the help of this, uh, we can say the protection of coastal infrastructure also can be done. Also, the surge storm mitigation can be done by the use of this one. Further, the sediment and accumulation can be done through this. Also, the flood retention, land preservation, and recreation protection can be done by this kind of structures. But we can say these kind of structures are very like these are rigid and heavy in, like we can say. So the cost, these are not that much of cost efficient. So in the replace of this kind of structure, we are going to use like a floating structure, we can say. So why we should use this kind of structure in the floating? So in the place of these fixed or rigid structures, we can use, why? Because these are some structures which are lightweighted. Also, these structures are flexible, cost efficient as there also, and also these kind of structures give the ease of assembly. We can like install in the different places in the very less time, or for the one place to another place also. Also, these kind of structures are very environmental friendly structures. Yes. So for my this study, these are some objectives which I have mentioned or done. So we are going to in this study, performance of scholastic flexible floating membrane has been done under oblique regular waves. Also, to study the impact of different bottom profile under the scattering, we can see here. Further, the different kind of structural and physical parameters I have taken, and the impact of this parameter on the wave scattering also analyzed here. These are kind of structure can be like membrane's length, also the damping parameter of the scholastic floating membrane. Also, I have considered here the oblique waves, so the angle of incidence waves we can consider, also membrane's tension I have considered here. Further, the different bottom profile also I have considered in the study. So this is my problem which I have considered here to study the wave scattering. So you can see I have considered here three different regions. So for the outer region, region 1 and region 3, I am using the eigenfunction expansion method. And for this inner region where the undulatility of the bottom is there, I have used the boundary engine method for this problem. Further, the length of this membrane is L, I have considered here. Yes, so this is the problem which I have considered in my study. Yeah, So going for the mathematical formulation, we can say that I have taken some assumptions to further proceed with this problem and some results and then conclusions. So I have considered here the fluid is incompressible, inviscid, and fluid is rotation. We considered, and further the problem studied here is Cartesian coordinate system. Further, the small amplitude water theory has been considered. Also, the motion considered is simple harmonic and time with angular frequency omega. So the only equation you can see here in equation number 1, where ky is nothing but the k naught sine theta. K naught is the wave propagation in the region 1 on the left hand side. Also, I have considered the bottom, rigid bottom I have considered here. So there is no penetration of the fluid across that bottom. So that bound condition for that one you can see as equation number 2, del phi 1 by del n, del phi by del n is equal to 0. Also, the different we can say bottom profile, which I have not written the equation, exact equation, due to the how can say that due to the save the slides. So I have considered here that also the free surface boundary condition, which is the combination of kinematic and dynamic free surface boundary condition, I consider here, which is dival phi 1 by del n minus k phi is equal to 0, where k is nothing but omega square by g here. Further, if we can say that the motion of flexible membrane, which is uniform in longitude direction. So the membrane deflection it can be expressed by the equation number 4 here. Yeah. Also, so the linearized kinematic boundary condition for this membrane also we can consider here is as del phi by del is equal to minus I omega zeta on the free surface. Further, the dynamic boundary condition, which I have considered here in equation number 6, where T is the membrane tension and the form of T you can see is nothing but real part of T into 1 minus I omega T, or we can say real part of T, not real part of T, like say we can say the storage modulo or the damping modulo, or the real or imaginary part we consider here. And tau is the damping parameter for this membrane, and n is the uniform average mass of the membrane. Further, I have considered that the edge end of the edge, or not end of the edge of this membrane, I have considered fixed. So there is no deflection we can say here. Also, further, we have considered for this two pseudo boundaries where x is equal to minus L on the left hand side and x is equal to R on the right hand side. So that's continuity of flow is there, or continuity of pressure and normal velocity is there. So by this boundary condition can be denoted by equation number 8. Also for Sommerfeld boundary condition, in equation number 9, you can see here, where phi naught is nothing but the incident wave potential denoted by this expression phi naught is x is equal to a raised to power I q naught 1 x into I naught, and q naught for both of the region we can see here is having this form k naught is j whole square minus ky square, and I naught is nothing but the vertical eigenfunction in the open water region. For left hand region, open water region means left hand region, right hand region, not the middle one. Also, k naught j is the positive real root for the dispersion relation. K is equal to small k hyperbole k h j, for j is equal to 1 and 2, means left hand depth, water depth, and right hand water depth. Now, by proceeding with the help of Green second identity, we are basically using the boundary element method here. So we are using the Green second identity here. So first, if we are having the boundary value problem with some boundary condition, which we have already described here, and we are having the fundamental solution. Now we can apply this Green second identity to formulate the boundary integral, and that boundary integral can be discretized into boundary integral equation, and those there we will find some kind of unknowns on the boundary. So with the help of the point collocation method, we can convert this boundary integral into system of linear equation to get the unknown data, and then we can get all the unknown data on this boundary to further calculate the results and conclusions. So after applying this Green second identity, we are having these reciprocal relations, and where G is nothing but this fundamental solution, and K naught is the modified zeroth order Bessel function here we can see, and also gamma is the value constant is having the value of 0.5772. Yes. After implementing this boundary element method, we are having this integral equation. You can see equation number 12 and 12. And this equation number 12 can be converted into a system of equation, which is generated by equation number 13. And that we are having this dynamic membrane dynamic boundary condition, which we need to solve with the help of finite difference method or central difference scheme we are using here. So which can be denoted by the equation number 14. So yes, by the help of boundary element method and the finite difference method, by coupling of this the finite difference method with the boundary element method, we can handle this dynamic boundary condition here. Also, there are some constants you can see in equation 14 where A and B are having the form of m omega square minus rho g by t, and B is having the form of minus I rho omega by t. And delta is the nothing but the delta of the j segment on the line on the boundary. Yes, so this model was validated by some of the existing research in the literature, where you can see Cho and Kim has done one kind of this problem. So with the help of that study, I have done that validation part also here. Yeah, and the seabed profiles which I have considered here, you can see on your screen that I have considered two types of different seabed profiles, the type 1 and type 2. So the impact of this kind of seabed profile on the viscous scattering we can see here now. So coming back to the coming to the results here. So you can see here that initially you can see I have we can say that there are some results on here for different value of the damping parameter tau. So initially when the value of tau is 0 here, so you can see Kd is the dissipation. So there is no dissipation of the energy. Obviously, there will be only the reflection and transmission in this case. But as the value of this damping parameter increases, there is the dissipation also increases, and the transmission reflection are decreasing. Obviously, there's a factor that as the dissipation is there, so reflection and transmission going down. Obviously, on the figure C and D, which are plotted with respect to the theta incident wave angle. In this case also we can say the initial when the parameter tau is damping parameter tau is 0, then there is no dissipation, but as the value of the damping parameter tau is increases, the dissipation also increases, but the reflection and transmission are getting decreases here. So and yes, yeah, here in figure 4 you can see 4 different value of the membrane's length, dimensionless membrane's length, which I have taken different values 1, 2, 3, 4, 5 I have taken here. So when the length of the membrane initially was 1, so there was like we can say in the short length assuming there was a reflection was less and then transmission also less. But as the length of this membrane as increases, and there is an oscillatory pattern of the reflection you can observe here. So it is happening basically when there's a reflection and the incident rays are like interacting with each other, then this reflection is showing this oscillatory pattern to that region. Yes. Further, the results for this different length of this membrane were plotted for the reflection, transmission, dissipation with respect to incident wave angle theta. So here you can see also initially when the membrane length was less, and when it was increased, the dissipation also increased because the more waves was interacting with this membrane, so more dissipation is occurring there. Here in this case, in figure number 6, you can see I have taken this T. Actually, this is T is the real part of T. This is typo error here. So this is the real part of T. So in this case, I have not considered the damping parameter, which I have already put it as is 0, the value of tau. So I have concluded this result to see the effect of this membrane tension on the dissipation, on the reflection transmission here. So initially, when the value of the tension was very less, we can say 0.01, then the reflection, we can say, oh, sorry, I have added here the also same results here. Sorry for that one. Here was the transmission also I have noted here. So the initial reflection is less, but as the value of the tension is increases, the reflection is get increases because the tension of this membrane is high. There will be more reflection will be there, as you can see. Further, for this ratio of this height on the right hand side as to by h1 I have taken here. So in the long wavelength regime with respect to H1, you can see here that the initially the reflection was high, but as the value of S2 by H1 increases in the long or we can say not intermediate but in long wavelength regime, this get decreases, reflection get decreases and transmission get increases. But the opposite pattern can be observed in the short wavelength regime here. Similarly, here we can see here for the dissipation, sorry, for the less minimum or less values of S2 by H1, initially the dissipation was high, but the pattern was got just opposed, and as the value of S2 by H1 increases, the dissipation get decreases here, and similar result can be observed here in the C and D also for the incident wave angle. Further, for the type 1 bed profile, I have taken here the parameter A1. A1 is nothing but the amplitude of this sinusoidal seabed here. So I have taken here 5 increasing values of this amplitude of the sinusoidal seabed here. So initially, when we can say initially when the amplitude of this sinusoidal seabed was less, there was a less reflection and less transmission was there. But this amplitude was increases up to 0.4. There's in the long wavelength regime, the reflection got increases and the transmission got decreases here. Yes, and a similar kind of results for this incident angle also added here. So as the value of here with respect to, we can say, incident wave angle, the value of this A1 by H1 or the amplitude is increases, the dissipation also increases here, and that's the transmission get decreases on the for the 0 to 40 degree of this incident wave angle. Here, yes, alpha. So alpha is nothing but this. Let me show you. Alpha is this kind of bed profile. So the different values of alpha, the different kind of different values of parameter alpha is I have taken here, which is -2, -1, 1, and 2. So in the long term regime here, you can see when initially I have taken this value of alpha is -2, so the reflection was less. But as the value of this alpha increases up to 2, the reflection get increases, transmission get decreases, and if we talk about the in short wavelength regime, so the reflection got increases and transmission got decreases, but the dissipation got increases. So this is also a factor of a good dissipation of the wave energy by the membrane for the different values of alpha. Here, the free surface elevation for the different values of damping parameter was you can see here in the figure 10a, and in 10b the membrane deflection mode of zeta by h I have plotted here. So when the damping parameter increases, the dissipation take places and the free surface elevation get decreases on the right hand side of this membrane, and the deflection also get decreases. Here you can see as the value of the tau increases here. These are some figure for the force for different kind of parameters, tau, then tension, membrane tension, then this sinusoidal seabed amplitude, and this m is the number of ripples of the sinusoidal amplitude. So this is the figure for the force, you can see here. So based on this study, we have concluded some kind of conclusions here. So for a horizontal floating flexion membranes, it was recommended to use a membrane's porosity in the range of 0.3 to 0.5 to ensure the transmission is to less than 30%. Further, the conclusion you can see on your screen. Here are the another 3 conclusions here. These are some references I have taken here. And thank you all for your attention. Thank you so much.
Thank you very much as well. So you've there's plenty of time for questions. Does anyone have a question? Maybe I can just ask a question myself.
Yes, sir.
So can you explain to me, when you do the boundary element method, how do you take into account this angle? Can you just show me that formulation? Like, when you go back to this boundary element method. So what's the Green's function is this
This
K
Green's function, I
naught.
have taken the fundamental solution here. We have
Yeah,
taken
that's
for oblique
right.
waves.
Yeah, that's right. Where does and Ky is the angle, the ratio of K.
KY.
Like I'm just on.
You are talking about, sir, KY, sir?
Yeah, the Ky is that as the angle, is that
Yes,
right?
KY is K naught sin theta. I have in the form, like initially I have shown here in this previous slide. So.
Yeah. And other people have done this, have solved this problem with this Ky, right? But okay, yep. So when you solve this problem, first of all, you set the omega, the parameter omega, and then that allows you to choose the Ky up to a certain value, right? Like what happens when the waves, if the angle became, say pi over 2, what would happen to the Green's function?
So in that case, like we are having this form of Green's function in this case. So we can say this when we increase the angle of incidence, automatically this Green function can handle through this equation, sir. Yeah.
Yeah. And what about that expression below? Surely that's an approximation, right?
Which one, sir?
So that one there on the bottom of that slide with the K naught, that's only for small r, right?
Yes.
Correct. That expression's only valid when r is small. Kailash, did you understand that question?
No, sir. No, sir. Please, can you please repeat it, sir?
You've written there that Bessel K naught of KYR is equal to minus gamma minus log of KYR
Yes,
over
yes.
2.
Yes, sir.
But that's only true if KYR is small, correct?
Yes, sir.
Yes, because it's not that what you've written there isn't, you don't ever say that KYR is small.
Yes, sir.
Yeah. I mean, so when you compared to these other solutions, they were for an incident angle of 0. Is that right?
For incident angle 0, sir.
No, you compared your solution to Orta.
Yes, yes.
Show me that. Yeah, there.
Yes, sir. Yes, sir.
What was the incident angle in those?
In this case, we have taken this angle as theta is equal to 0, like normal incident rays. Yes, yes.
Yeah. But if go back to the Green's function, surely if theta is equal to 0,
Yes, sir.
isn't Ky 0 then?
Yes.
So how does that work?
No, I don't want to make any kind of comment on this right now, sir. Let me see about this one.
Okay.
Yeah.
All right.
Yes.
Is there any other questions? I've been in a bit of a grilling. I'm just trying to understand it. Does anyone have any other questions? I'm not hearing anyone else. So we've got a few minutes to wait, and maybe we'll just wait